When drawing Lewis structures, again, a Lewis structure is just a 2D model of how the atoms are actually connected to each other within an ion or a molecule. When doing them, though, sometimes it's easy, relatively speaking, to tell if we need a multiple bond somewhere because we need to give that central atom its octet. But what if we can't always tell? Or what if we're going to an expanded octet? We use formal charge to decide this. Formal charge tells us how happy or stressed each atom is with the way the electrons are being shared in the Lewis structure. It's a bookkeeping tool. It's not necessarily what's really happening, but a way for us to check whether our drawing makes chemical sense. So, kind of an example is let's think about a neighborhood analogy. Each atom is like a household in a neighborhood. The overall neighborhood is your molecule. The electrons are the residents. Atoms own certain electrons, their valence count, okay, so they have their own electrons, but in molecules, they may share fences, like a bond, or have roommates, which are your shared pairs. Formal charge tells you who's hosting extra guests, giving it a negative charge, who's missing some guests, giving it a positive charge, who's got the right head count, zero charge. Again, if that doesn't make sense, that's okay. I'm just trying to find an analogy outside of chemistry, but we will pull it back. We will show it to you with the molecules in a sec. Basically, too many or too few guests creates tension in the neighborhood, so atoms with charges create a reactivity, more likely to react within the molecule. Chemistry happens because atoms want to balance out those charges. They want to move electrons to make everyone content. So the best Lewis structure is going to minimize the formal charge and place the negative charges on the most electronegative atoms because they can best handle the negative charge. When multiple Lewis structures are possible, we're going to see that in resonance in the next module. The one with the most balanced formal charge is the most significant. It's the one that contributes most to the real structure. Areas with formal charges often show where reactions will occur and where positives attract negatives. So, how do we do it? Formal charge. The sum of the formal charges must equal the overall charge. I will talk about this in the example in just a sec. Sorry, making sure I've got colors on we can see. I will talk about this in just a minute. Okay. What I mean by that is like if I look at the nitrate ion, which is down at the bottom of the screen here, if I look at nitrate, when I draw this out, the overall formal charge of each of the molecule has to equal up to a -1. Okay. I'll show you that one in just a sec. Formal charge of an atom is defined as the number of valence electrons on the atom minus the number of electrons assigned to the atom. Okay. Let's figure that out. The number assigned corresponds to all of the unshared electrons plus 1/2 of the shared electrons. Okay, we'll figure that out. Here's the shortcut. To find the formal charge, you take the number of valence electrons you have on that specific atom. You subtract the number of lone pair electrons it has. You subtract one for every dot. And you subtract one for every electron shared. So if you have a bond that's sharing 2 electrons, half of that goes to the atom. So it's every bond is one line. I subtract one for every dot and one for every line. And I'll show you what I mean by that in just a sec. So I'm going to move this up just to give us some space. So let's look at nitrate. NO3 minus. Nitrogen has 5 valence electrons. I have 3 oxygens at 6 valence electrons each. And then I have that negative charge, which adds one more valence electron. Remember, negative adds an electron, positive removes an electron. So 3 times 6 is 18, plus 5 is 23, plus 1 is 24. I have 24 valence electrons I need to distribute. Remember, your more electropositive or less electronegative atom goes to the center. I know my electronegativity trends. I know fluorine is most electronegative, oxygen is in second place, and nitrogen and chlorine are tied for third, which means nitrogen goes center. Connect all the atoms. Okay, so I've connected all the atoms. Now, give your outer atoms their octet. Now check how many electrons you've used up. We've used up all 24 electrons. Now check our central atom. Our central atom does not yet have its octet and it needs an octet. So remember, there's only a few atoms that don't get their octet, like hydrogen, beryllium, aluminum, boron. So the nitrogen needs its octet. So to give its octet, we're going to take a pair of electrons away from one of the outer atoms and make a double bond to the nitrogen. We can't just give those electrons away because if we gave it away, the oxygen would be missing its octet. Instead, we're going to take it from the oxygen and form a multiple bond to the nitrogen. Now, the nitrogen has an octet, All of the oxygens have octets. Now, you may be asking why I put the double bond there, not in a different spot. That is resonance, and that is coming in the next module. But I could have done that as well. I could have put the double bond here, or the double bond here. All of these are valid Lewis structures, and so we will talk about resonance in the very next section. Negative charge. Sorry, I'm trying not to make it so close. It's a negative for the overall ion. So this is the Lewis structures. And again, we're not dealing with resonance right now, that will come soon, but let's talk about formal charge. Let's just label these 1, 2, and 3 for the oxygens, okay? And I'm only gonna do the first one because you can see that it will correlate to the other species as well, and then the nitrogen. Let's look at nitrogen first. Nitrogen has 5 valence electrons. I'm gonna subtract 1 for every dot that is only on the nitrogen. It doesn't have any dots. Remember, each dot represents 1/2 of the lone pair of electrons. So it doesn't have any dots, so we subtract 0 for that. And then I'm going to subtract 1 for every line on the nitrogen. The nitrogen has a +1 formal charge. Oxygens 1 and 2 are equivalent in their structures because they each have 3 lone pairs and 1 bond. Oxygen overall has 6 valence electrons. I have 6 dots on the oxygen, and I have 1 bond to the oxygen, giving me a -1 charge. I'm going to draw those in a different color. So -1, you can't see the color very well, but -1. And then oxygen 3 has oxygens always have 6 valence electrons, but the third oxygen has 4 electrons on it and 2 bonds. So an overall 0 formal charge. So notice in this molecule, and this is the right structure, the nitrogen has a +1 charge, 2 of the oxygens have a -1 charge, and 1 oxygen has an overall 0 charge. So +1, -1, -1, plus 0 gives me an overall -1 charge. This is what it means by this statement here. The sum of the formal charges must equal the overall charge. So overall, the sum of all the individual charges is equaling -1, which is the charge on the nitrate ion. So memorizing 0 formal charge can be helpful. I find this to be really helpful. So we might as well do it. It will speed it up so you don't have to count them every single time. Okay. And there are other trends you're going to find as well. So, like if you have a halogen that has a single bond and 3 lone pairs, it has a 0 formal charge as well. Okay, so there will be other trends you find. And I want to say that these trends go for the elements underneath them as well. But if carbon has 4 bonds, 0 formal charge. Carbon wants 4 bonds, always. It doesn't mean it always can have it. Sometimes it will have a lone pair, but carbon would prefer 4 bonds. That could be 4 single. It could be a double and a single, or double and 2 single. I apologize. It could be a triple with 1 single. It could even be 2 double. If I see carbon having any combination of 4 bonds, I know it is a 0 formal charge, and I'm not even gonna count it at that point because I just recognize it. Nitrogen, if nitrogen has any combinations of 3 bonds and 1 lone pair, it will have a 0 formal charge every time. This holds true for things like phosphorus as well, because it's right underneath nitrogen in the table. Oxygen, oh, again, yes, that could be 3 single with the 1 lone pair, 1 double, 1 single with the 1 lone pair, or 1 triple with the 1 lone pair. Any combination of 3 bonds with a lone pair on nitrogen or any element underneath it, so like phosphorus is underneath it, would have a 0 formal charge. Oxygen will have 2 bonds and 2 lone pairs if it has a 0 formal charge. So 2 single bonds and two lone pairs, or one double bond and two lone pairs. And again, this holds true for the elements beneath it as well. So things like sulfur, same situation. If it has two bonds and two lone pairs, it has a zero formal charge. So let's determine the formal charge on each atom in these molecules. Well, first, we have to draw them. So NH4 plus, remember that it's called ammonium. It's your ammonium ion, it's polyatomic. Nitrogen has 5 valence electrons. I have 4 hydrogens, each at 1 valence electron. But notice I've got a positive 1 charge here, which means I need to subtract 1 valence electron instead of adding it in. So 5 plus 4 is 9, minus 1 is 8 valence electrons. Now, nitrogen has to go to the center here. I realize electronegativity-wise, it's more electronegative than hydrogen, but hydrogen cannot have more than one bond. Ever, no exceptions. It does not have space for it. So remember, hydrogen can only have one single bond. And if it has that bond, it has no lone pairs. Hydrogen can only hold 2 electrons total. And that bond is it sharing 2 electrons, so it's holding on to 2 electrons. So connect my hydrogens. I've used up 8 electrons, and that's how many I have. My outer atoms have the equivalency of their happy octet. Hydrogen can only have a duet. So that's where we're stuck for there. And nitrogen has its octet. This is the correct structure of ammonia, or ammonium, I apologize. Let's look at formal charge. Well, hydrogen, 1 valence electron, 1 line, so 1 bond to it, and 0 lone pairs. Let me put those in the other order so they match what the slide is above. So 0 lone pairs of electrons, or 0 lone electrons to it, and 1 bond to it gives me an overall 0 formal charge, and all the hydrogens look the same. Nitrogen, 5 valence electrons. It has no lone pair electrons on it, so no lone electrons at all, and 4 bonds to it, an overall +1 charge. If I add this up, 0 plus 0 plus 0 plus 0 plus 1 gives me an overall +1 charge, so it adds up. Let's look at carbon monoxide. Carbon, 4 valence electrons. Oxygen, 6 valence electrons. Overall, 10 valence electrons. So I've got carbon, bond to oxygen. Now, it doesn't matter which species you give the other electrons to right now. Just put them out. 2, 4, 6. I've used up 8. Put my remaining electrons on the other atom. Now, my oxygen has its octet, but my carbon does not have its octet yet. So I need to take a pair of electrons from the oxygen and make a multiple bond. Oxygen still has its octet, but carbon does not have its octet yet, and it needs it. So I'm going to take another pair of electrons from the oxygen and make another bond. The most you will see is a triple bond, and we'll show how these actually look in space in the next chapter. But I've got the carbon triple bonded to the oxygen, and each one has a lone pair. They all have their octets. So this is the correct Lewis structure. But let's do formal charge. Carbon has 4 valence electrons. It has 2 lone electrons on the carbon atom directly, and then 3 bonds to it. So an overall -1 charge. Oxygen has 6 valence electrons. It has 2 lone electrons on it and 3 bonds, and overall +1 charge. Now, when I add these up together, +1 -1, it equals out to 0. So the overall species does have a 0 formal charge. Yes, most of the time we try to put the more negative formal charge on the more electronegative element. So we'd want that negative charge in oxygen, but we can't do that because everyone needs octet. This is the correct structure. We can't change it. Carbon monoxide is a nasty little molecule. Its formal charge is not the greatest either, but this is the correct structure with the correct formal charge. Now, let's go ahead and draw SeOF2. And since my good notes updated, I don't know where all my functions are anymore, so I'm just going to make some space for us. I apologize. I really should figure out the new update happened, and now I don't know where all my buttons went. I don't know how to use them all. I haven't taken the time. So SE, Selenium, actually, I forgot what selenium is, so I need to look up on the table. I don't know where that is in the table. Like for number of valence electrons, I think it's 6. Let's check. Yes, selenium is under sulfur, so 6 valence electrons. I know oxygen has 6 valence electrons. I have 2 fluorines, and I know fluorine has 7 valence electrons. So 7 times 2 is 14, plus 6 is 20, plus 6 is 26. 26 valence electrons. Selenium's going to go to the center because it's the least electronegative. How do I know that? Because I know that fluorine is first and oxygen is second. So therefore, it can't be higher than those. Connect all of my atoms, fluorine and oxygens. It doesn't matter which spot you put them in. I just like my molecules to look symmetrical. Okay, it doesn't matter at all. If I could have put the oxygen on the side, the fluorine on the top, that doesn't matter at all. Give your outer atoms their octet. I've used up 24 of my electrons. I have 2 remaining, so I'm going to put them on the central atom. So I put them on here on the selenium. Now everyone has their octet. So now I need to check formal charge to see if I need to make any double bonds anywhere. So let's look at the oxygen first. Oxygen has 6 valence electrons. This oxygen has 6 lone pair electrons and 1 bond. It has an overall -1 charge. I'm not going to change it yet, but there's a good chance I'm going to use that to double bond to something. If I look at my fluorines, fluorine has 7 valence electrons. It has 6 lone pair electrons and 1 bond, overall 0 formal charge. Now, I didn't even have to really count that up because I said if a halogen has 1 bond and 6 lone pairs, it's going to have a 0 formal charge, but better to check it than not until you guys get comfortable with that. Also, like hydrogen, fluorine can only ever have 1 bond. It can't have the expanded octet because it's an N equals 2 energy shell. So even though we don't say it as an exception, fluorine can only have 1 bond. You'll never find fluorine with more than that. It can't do it. And selenium. Selenium has 6 valence electrons. I have 2 lone pair electrons on there, or sorry, 2 lone electrons in 1 pair. So 2 electrons, 2 dots, and 3 bonds. Give me an overall +1. Now, the structure overall is telling me that like +1 -1 equals out to 0, which is correct, but I can minimize that formal charge. And I'm going to do that. I'm going to take away one of those lone pairs from the oxygen, make a double bond to the selenium. Now, if you recheck your formal charge, oxygen now has 4 electron dots and 2 bonds, and overall 0 formal charge. Selenium now has 2 dots, 4 bonds, and overall 0 formal charge. So this is the correct structure for SeOF2.